Hi there. In this hopefully short video, I will discuss about list versus set in Python. Most of you would have already worked on list in Python and you know how to create a list using little notation. There are different ways you can create a list. You can create a list by using a is equal to 10, 20, 30, which we call this little notation. You could also use a list constructor to construct a list if you want to, right? You could also set a is equal to list of range of 10. This also creates a new list. There's a third way to create a list which involves using comprehensions. You could actually say a is equal to value into value for value in be in range of 10. All of these create a list, right? The first one is a little notation of a list. The second form where you use a list construct. Many of you are new to Python. This looks like a function call. List looks like a function call, but let me tell you, constructor expressions look like function call in Python, right? List is a class. When you open and close parentheses surrounding a class, you're invoking it like a function, and that is how you construct a new object of the class, right? So here, this is a constructor expression. And the last form is a little interesting. This is called as comprehensions. For those of you who are not aware, I will do a separate video on comprehensions to cover that more in depth. But for now, it is suffice to know that many collections, especially the built-in data types, you can construct them using this expression, where you want to say what you want to store in this particular list, result of this expression, for element in iterable. That is a syntax. This looks like a for loop, right? It has similar to a for syntax, but let me tell you, this is used as an expression, not as a statement. That's why it's called as a comprehension. In this case, it's called as a list comprehension. You could also create a set the same way. You could, I'll just print the variable in here. I'll print the variable also in here. And you can see the result. Just like there are three ways to construct a list, there are three ways to create a set. So I'm going to show you how to create a set here. I can use curly braces instead of square brackets to create a set. I'll make it a little more elaborate with more numbers. I could also construct a set by using the set constructor. The set constructor will take any iterable object as long as the iterable object holds hashable objects. Range gives you numbers which are all hashable. Okay, by the way, even for a list, you can construct a list from any iterable object. There are no rules. If you can iterate over any object using a for loop, you can always create a list from it. You can also create a tuple the same way. Okay, so they all are quite consistent in here. So let's say a is equal to set of range of a. So let's say range of 10. This actually constructs a set using a constructor expression. Range objects are compatible. You can construct a set from range object without a problem because range only gives you numbers when you iterate over them. You can also construct a set using comprehension expressions by using curly braces like this, and even this works. This is a set comprehension. Pretty much the same, right? Quite similar. The one peculiar thing you should note is that the elements look very orderly when you actually use range. Just observe that. A set construct is a little optimized when you're dealing with range object. The elements orders are maintained as it is. See this? It's fully in ordered form. But if you do this in another way, let's say a is equal to list of range of 10. This time you can see that a is a list, shown up in square brackets. If I now try b is equal to set of a and try to print b, oh, even now it's in orderly manner. It's quite orderly, right? So you can see this. So even when you have a list of orderly values, when you create a set out of it, it looks quite orderly. So there, but if you try to create them in the literal notation, let's see if I can do it in literal form. If I try to say b is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Print B. Oh, even now it's orderly. So right now when you see numbers which are in equidistant step values, right? Like 0, 1, 2, 3, 4, 5, 6 things, numbers like this, it works. But let's try with numbers that comes up as, let's say, 10, 20, 30, 40, 50, 60, 70. Yeah. Do let me know why is this the case, right? Okay, again, if you know the answer why this was maintained in the orderly manner and why this is not maintained in the orderly manner, do post them in the comments, right? I'll leave that as an exercise for you to explore on. Coming back, you might now ask me, when should I use a set, when should I use a list? List is quite convenient to use. It's a very commonly used data structure alongside with dictionaries, of course, in Python. But there are certain use cases where set is preferred over a list. I'm going to show you the differences. One of the common things about list is when you create a list of numbers, and let's make it a little random. This is a list of sort of random numbers which you can see. Now from this particular collection, I want to find out whether a particular number exists. I want to check whether 55 exists in this list. How do I do that? Well, if you think you should be using a for loop and iterate over it and compare, no, that's not the right way to do it. In Python, every collection supports a special operator called as an in operator. It's a built-in feature in Python. So every collection supports this. So if I want to check whether a value, let's say 55, exists in this list, you might want to say just 55 in A. Instead of rewriting a for loop, Python does it for us. It's actually not Python language runtime. Basically, this in operator gets this 55 in A gets translated as A dot double underscore contains of 55. This is how it gets compiled. So which means that there's a special method in a list. There's the under method that you see here called contains. So the list object implements this method, and this method is a responder method for the in operator. When you use in operator, the responder method is this, and this is going to check whether 55 is there in this list. Even a set has a similar feature. I'm just going to paste this. A set is unordered. And say print A, the order is lost. You cannot ask give me the first element or the last element or any nth element. So set is not subscriptable, right? I already covered that in one of the earlier videos. You go have a look into the video if you have not. But then here, if at all I say 55 in A, when this works, you can always check whether an element exists in a set. And this is one interesting aspect. Searching for element in a set is extremely faster than doing so in a list or even a tuple. We're going to compare that. One of the ways to check for performance of any expression or statement, if you're using something like Jupyter Notebook or if you're using IPython, we have this interesting magic called time it. Using time it, you can find out how much time a particular expression takes. And this time it magic does all the interesting things like running the expression a couple of hundreds or thousands or even a million times if necessary to get more proper averages, right? Which is fairly accurate in most cases. So what I'm going to do now is I'm going to get a list. I'm going to say A is equal to list of range of 1000. I'm also going to create a set like this. B is equal to set of range of 1000. So I have two collections, a 1000 element list and a 1000 element set. And I want to check for existence of the last possible value in it is 999, right? I want to check for that in both the list and a set. I want to find out how much time it takes. So I'll just try time it 999 in A percentage time it 999 in B. If I run this cell now, it's going to take some time. As you can see, an asterisk here indicates that it's computing. All right. You can see that the time it magic for this expression, what it did was it executed this expression. It ran this expression about 100,000 times into 7. 100,000 into 7 times. 7 runs, 100,000 loops each. And tries to get the average time taken from there. It says mean plus or minus standard deviation of 7 runs. It says it took about 5.58 microseconds. You can see that microseconds plus or minus 278 nanoseconds per loop. This is for a list. So it took about roughly 5.5 microseconds to figure out whether this so and so element which you're looking for, let's say 999, is there in a list. Even for a set, when you try running this, you get the same kind of result, but you can look at the output here. It ran more number of times because the first time it executed, it figured out that it actually occurred in this expression took only about few nanoseconds, then it went more number of iterations to get better averages to avoid all the operating system jitters and all that. So in this case, you can see on average it took about 39.4 nanoseconds. You can see that searching for an element in a set is many magnitudes faster than doing so in a list. I'm going to just increase the size of this list and a set by 10 folds and demonstrate this again. This time I'm going to make this list have 10,000 values, set 10,000 values. I'm going to look for 9999 in list, 9999 in set, and try running this now. Alright. If you closely observe, roughly, it took 10 times more. From 5.58 microseconds, it went to 57.5 microseconds to search for the element. This is from the bigger notation. You can think of it as O of n complexity, right? It's linearly growing. So the more the size of the list, worse complexity. It will take more time to check whether an element is found or not in that collection. Whereas in a set, they observe there's not much of change. From 39.4 nanosecond, it just went to 47 nanoseconds. It's close to 01. It doesn't matter. If you even increase this number by another 10-fold, you'll still see for a list, it's going to take more time. But for a set, it's almost going to be consistent with very minute changes in time. So you run this one more time, increase number to 5 digits, 5 zeros, that is 5 zeros, and searching for 5 nines, right? It went more than 10-fold here. You see that? 632 microseconds. But for a set, it's almost the same time, roughly the same time. So what you see here is that searching for element in a set is almost of O1 complexity. It doesn't matter whether a set has 10 elements or 10 million elements. Searching for elements is almost going to take uniform time. So you can assume that a set is a collection optimized for searchability, right? Not just that, a set provides a lot of convenient features. If you want to use collections for comparison, set is a right collection to use. It's an optimal collection for comparing. That's why it's called a set. In fact, you know about set theory now in a while. So let's say I have 2 lists now. Okay, I'll take the list which I created earlier. Let me just take this. I'll also create now one more list which also contains quite random numbers in here. So let's say it contains 18, which is already there in A. I just chose that. And 43. Okay, 43 is there. Let me make it 42. And 67, 56, 23, 89, then let's say 10, then 76, then 50, 58. I'll add one more number. Let's make this almost identical size. Let's try 63. Now there are 2 lists. Sometimes I want to find out what elements are there in list A that is not there in list B. If it's a list, you know what you need to do? You need a loop. So you could say for value in A, if value not in B, I could actually have a result which will have an accumulation of all those values not found. I could say result dot append of B. Ultimately, when I try to print result, these are the elements that is there exclusively in A but not found in B. Right? If it were a set, if these both collections were a set, I'll tell you how easy it is to actually perform something like this. I'm just transforming these two collections to a set. You don't have to write this complex logic in here. For loop and if condition inside and all that. All you need to do is just say A minus B. We call this set difference. You could also find out what is there in B that is not there in A just by reversing the operands. Same thing, set difference. Elements that's found in B, not found in A. You could also try A ampersand B, which is set intersection. What is set intersection? The common elements found in both A and B. What elements are there commonly both in A and B? Very easy to find out. But where a list, you need a loop and a condition inside it. One loop is what we write, which will be interpreted. Another loop is implemented within the list construct that contains method level loop on its own. You go and search for that, right? So it is actually quite complex. Whereas here, it's all done with simple operators here. So we try to say set intersection. You can see this is a set intersection. To make sure it looks intuitive, I'm just going to write nice print statements in here. So I could just say you see that B minus A is this, and this is set intersection. So let me put a format string and in curly braces I say A ampersand B equals close curly braces. If all I want to get union of two sets, you can just look at the relation here. You concatenate lists and tuples. In general, you concatenate sequences. You merge two sequences to create a new one. But what about sets? You don't really concatenate, you create a union of them. Sets, elements cannot be duplicated. So when you create a union of two sets, duplicate elements, you'll see them only occurring once in the final set. And the element ordering is lost, right? So if I do that, I could just simply say A pipe B. The pipe symbol performs set union operation. You can also do something more exotic like symmetric difference. If you learned set theory in academics, I'm sure you know what symmetric difference is. It is basically the elements found in A, elements found in B, but not common to both. It's represented as A union B minus A intersection B. I can still remember my elementary schooling set theory. So if you know about that, I think this is what it is. And to achieve that in Python, you could just say A cap B. This will work as symmetric difference. Not only that, let's consider one more smaller set. Let's add C here. C is equal to, let me just add some numbers. Let's say 23, then 10, then 76, then 58, then 42. I want to check whether all the elements of C is there in A, whether all the elements of C is there in B. This is called a subset operation. Checking whether C is a subset of A or C is a subset of B. And how do I do that? Straightforward. I could just simply say C less than A. C less than A. This expression does it. This is called subset operation. I'll also try C less than B. It's called subset. This will return either true or false. Looks like C is not a subset of A. It means that all the elements of C is not found in A. There are some elements of C that is not there in A. But C is indeed a subset of B. In fact, when I created C, I just took up some numbers randomly from here and I constructed it. If you just verify, Not all numbers which you find in C is found in A. I don't think, 23 is there, 10 is there, 76 is there, but I don't think 58 is there. There is no 42. 42 and 58 is not found in A. But you'll find all these numbers, 23, 10, 76, 58, 42, all of them are found in B. You can see that? 23 is here. You'll find them in here. 10 is also found. You can find 76. You can find 58 likewise. 58 is, 58 is found in here, right? And 42 is there here. And this is a sure short way to check that, right? The exact opposite of it is superset operation. You could actually use an expression like, say, A greater than C. Check whether A is a superset of C, or check whether B is a superset of C. This is a superset operation. Yes, these are some of these operators that are supported on a set. It is not applicable to a list or even a tuple or any sequence for that matter. Some of you might ask, okay, this looks very mathematical. Is there any practical use for this? Consider it this way. Imagine that you're building a shopping cart for an e-commerce site. The middleware, maybe the customer does, select some items from the cart, select some items from the inventory and adds it to the cart. Maybe the customer buys some products, is added to the cart, and the final thing is going to do is checkout. When you perform the checkout from the cart, at the middleware or at the backend, if it's done in Python, you'll be doing set theory operations sometimes. You might want to check which products need to have this 40% discount or 50% discount, right? You do the comparison. You don't want to write a loop or, explicit condition check and all that. You apply set theory. You have a list of you have a collection of products in the inventory which have discounts, and you'll see whether this cart has such products. You apply them. Or you want to check whether the product that the customers added is repeated. So all those are, obvious set is unique, right? So all of these comparison can be done in set theory. Or another example I can think of is in, let's say you're building your own test suite where you're trying to run some test cases, right? So you run 2 iterations of test cases, and the result of it you have in collections. Result of first test case, result of second test case. You want to compare these 2 results. What tests are passed in the first test case, first test iteration, what are not passed in second iteration, or what tests have passed in both the iterations, right? So these kind of comparisons are easy to perform if you consider using a set. The final thing I should tell you is that a lot of features in a dictionary now, especially keys of a dictionary and items of a dictionary, can be treated like a set. All these operators in Python 3, especially Python 3.6 onwards, will work on keys of a dictionary or also on items of a dictionary. I would want you to explore that. If time permits, maybe when I talk about dictionaries in the future videos, I'll also give you some insight onto it. But point is, you can do this kind of comparisons even on dictionary collections, right? So this is something you should know about between the difference between a list and a set. Obviously, there are drawbacks with a set. Drawback number 1, they are not subscriptable. Drawback number 2, it can be treated as a drawback because you cannot have repeated element. Sometimes there could be a necessity where you want to have elements repeated. You can't use a set for that particular use case. And final drawback is though the set is actually fast in comparison and in searching for elements and so on, it does take more memory than a list. Now, if you just look at it, let's try this. If you want to find out the memory usage of any object in Python, look no further. Just learn how to use sys module. This module has sys.getSize of function, which will tell you the memory footprint of any Python object. So if I say sys.getSize of A, for example, that's a set which I created earlier. It took about 728 bytes. I'm going to print A. Just show you that set. If I convert this to a list, if I just say B is equal to, or I'll say maybe A1 is equal to list of A. Remember, some time back I told you can always create a list from any iterable object. A set is an iterable, being a collection. You can always create a list from it. So if we just say now print A1, it's a list. But if you want to find out the size of it, you will just try to say this dot get size of A1. Let me try to make this look a little more consistent. you can see that a set is many folds larger than a list. I mean, a list set is bigger than a list in here. Let's try with this range examples, right? If I say A is equal to list of range of 1000, I'm not say print A because I don't want to flood my screen with 1000 numbers. I know there are 1000 numbers in this list. We should just verify, you should just confirm that. We can say len of A, will tell you 1000 numbers. And I can also find out the memory footprint of it by using sys.getSize of A. I see that it takes roughly about 8 kilobytes. We try the same with a set. B is equal to set of range of 1000. Print len of B, sys.getSize of B is at least 4 times bigger. Yeah, there is size complexity when you're dealing with a set. And in the early days, I remember, I think as the modern version of Python, they have optimized a lot of features in it. But in the early days, when you actually do things like add, remove elements from a set, the set size just increases. It doesn't shrink. So we need to use some weird hacks where we need to, at some point in time, reassign a set to a new object, destroying the old object to free memory. So it seems like a memory leak. It's because the way the array buckets and hash buckets are maintained in a set. New buckets are created for storing new elements. When you remove the elements, the buckets are not removed sometimes because some other element exists, but there's a lot of free gaps in between. Basically, it leads to a lot of internal fragmentation when getting a set, and that can actually make set grow in size. They have taken care of reducing that. I will not say fully avoid, reducing that problem. The newer editions of Python, I'm not seeing that kind of problem since Python 3 or 4 at least. I've not really gone through the source code, but I believe they have come out with innovative algorithms to, optimize creation of new hash buckets perhaps for a set. There could have been some improvisation, but in early days this was a problem, both for a dictionary and a set, right? Anyway, so this is a small video where I try to cover the difference between a list and a set, and you know the difference now. In summary, if you want to compare collections, try using a set. If you're not really worried about comparing collections and you want to just maintain elements the way you want it to be, then a list is preferred, right? And list takes up lesser memory than a set with the same elements in place, right? All right then, so thank you all. Hope you enjoyed this video. So if you do have any questions or any queries, or if you want me to do any other video, any more videos on the similar topic, do comment. So I'll be looking forward to it. Thank you very much.